as you guys have realized, and I've told you, I'm still not Captain Forbes. You guys get me for one more week this week, but then he should be back next. You should get him back next week, unless he manages to have a third child this weekend, which would be very impressive. But it sounds like he should be good. So you will get him back on then. Until then, it is still you guys and me. As a quick reminder, you guys got homework and lab due on Wednesday. So focus on getting that done. And then as a reminder, we are not meeting on Friday because we have not really a 3-day weekend. It's no class because of NLCS. I have to keep saying that. My brain slows down every time I say that because I want to say NCLS for the national champion, but no, it's NLCS, right? Yes, National League. Okay, yes, NLCS. So I will not be there. Before we get into the meat of what is I think, really cool lesson, anyone have any admin questions or want to give me a hard time that I have needed a haircut for a really long time and just got one yesterday? Now's your time. Strangely enough, in this COVID time, my haircutter has been my wife, and ironically, it is harder to get an appointment with her than it was with a regular haircutter outside. Although she's still much nicer than at the Pentagon. The Pentagon has down on the first floor has a barber shop, but because of how many people go through it, it is the most streamlined. Like get a good haircut. But the lady who cuts my hair down there is all about getting done fast. So it's almost like a cartoon where she just spins it around and does it. She just grabs your head and does not treat you like a human being and just gets it done and then says, all right, pay money, get out. So it's great. But my wife's bedside or chairside manner is much better. Okay, so with that, we are talking about confidence intervals today. And so last week we introduced the kind of theoretical ideas of sampling distributions and the central limit theorem. And all of that was so that we could get to doing actual useful things like the confidence intervals and hypothesis tests. And so just like last week was really the important theoretical foundation. This week is going to be the gist of what we're going to be doing for the rest of the semester, just in different versions. So definitely take the time to interrupt me and ask questions if I say something that sounds strange or doesn't make sense. But like I said in the guided lesson, confidence, if there's anything you have seen before, if you've actually seen a statistical method, it's probably confidence intervals, right? Because they are around us all the time, right? A confidence interval is for, like I said on the screen there, if we don't know the actual parameter P, we can take a single sample, an estimate, a point estimate, a single point on the number line, and estimate it with P hat, right? But the problem is that a lot of times that is not great. Like you guys we're all statisticians here. And so if I tell you, hey, I've got a point estimate P hat of P that is, 3.5 with a sample size of 100, you know what that means. And you can decide whether or not that's good, bad, or somewhere in between, right? But to your normal person, if they say, hey, I'd like to know what proportion of, let's say, what's the proportion of cadets at the academy who are male? And I say, well, I don't know, but my estimate is 52%. They are going to look at me like, okay, well, I asked you what it is. You just said you don't know, but that's your guess. And as a statistician, you're going, no, here's all my estimates and everything. What a confidence interval does is it gives us a really kind of concise way to summarize not only our estimate, but a level of certainty around that estimate by building an interval around it, right? So to cut to the chase and spoil, what we're going to do is say, here is my estimate, and then I'm going to build a range around it, and I'm going to say how confident I am that the actual number is somewhere in this range, right? And if you've ever watched election night before, you've seen a confidence interval, right? Because when they say, hey, when CNN says, hey, we're predicting 62% of America is going to vote for Colonel Richards, they don't actually know that. What that means is they took a sample of 100 or 1,000 people, and 62% of them said that they were going to vote for me. If you look at the small print down on the TV screen, usually it'll say something like margin of error is 2%, right? And so they're not saying it, but what they're saying is we are confident that the real number is somewhere between 60% and 64%. They've built a confidence interval based on their numbers, and that's what they're trying to say, right? So we're going to talk about how to actually build them and what that means. All right, before we get into the math of an example here, anyone have any questions about generally what a confidence interval is and why we would care about one? Awesome. Okay, so this example, like all examples, is a little contrived, but let's use this and say a website is trying to increase registration for first-time visitors, so it exposes about 1% of the visitors to a new site design. So doing that, out of 752 randomly sampled visitors over a month of people who saw the new design, 64 of them registered. So what we want to do is construct a 90% confidence interval for the fraction of first-time users of the site who would register under the new design, assuming everyone acts the same way. So basically, I want to know what's the real percentage of people who would register for this new site. I don't have time to ask everyone, so I took a sample of 752 people, saw how many did, and now I'm going to try to build an estimate and an interval around that estimate. So our goal is going to build a 90% confidence interval around the actual percentage of people who would register if shown the new site. And as I read what I wrote here, this is probably not the most accurate way of saying it, because it's not really that I am building a confidence interval around the actual percentage. What I want to do is I want to build a confidence interval, let's say, that captures or that includes the actual percentage, right? Because I'm going to build an interval, but I'm not going to say the interval has to be centered right around the actual number. If that was true, then I would just know what the actual number is. What I'm saying is I'm going to build an interval that I believe the actual number is somewhere in there, maybe at the very low end, maybe at the high end, maybe right in the middle, right? But it's just that I'm hoping to capture that real number somewhere in there. Okay. Then my sample, right? My sample is that 752 people, right? I showed 752 people the new site, and out of them, 64 registered. So out of that, I know that I still don't know the actual percentage of people because I only showed 752, but my estimate, my point estimate, my p hat is 8.5% because 64 divided by 752 is 0.085. Hold on a second, I'm a wuss. I'm going to turn on the AC in my office because it turns out the sun is shining through on me, and I grew up in Northwestern Washington, and I'm a baby when it comes to heat. Okay, so that is our estimate. The next thing I want to do is I want to check my conditions, right? Because everything we're going to do depends on the central limit theorem. And so I really don't want to use the central limit theorem, but I have to prove that I am allowed to use it first, right? And so we have those two conditions. The first condition is that, and I didn't write it here because I was focusing on the math, but the first condition is, are our observations independent, right? And we have this right here, randomly selected visitors. So it is met, right? Because if I was writing this up in a lab, I would write a line, our observations come from a random sample, therefore they are independent. Done. Condition one met. Condition two is pertaining to, is our sample size sufficiently large? And we've shown before that the way we do that is we check the two inequalities, right? N times P has to be greater than or equal to 10, and N times 1 minus P has to be greater than or equal to 10. And N times 1 minus P is 688. Those are both plenty bigger than 10, so we are good to go. So our two conditions are met, which means the central limit theorem holds, and I can do everything I am wanting to do after this. So before I start doing said things, anyone have any questions on what we have done up to this point? A lot of this is what we were doing last week, but I want to make sure that over the weekend, not too much of it fell out of your head. So is there any questions or any reclarifications that anyone wants or needs before we move on? Awesome. Okay, so then we can go ahead and calculate our standard error. And again, the standard error is usually calculated using P. We don't know P, so we're allowed to use P hat. So this is my equation for the standard error of P hat, and I get a standard error of 0.01. And as a reminder, what the standard error is it is a measure of how much variability there is in our estimate, right? It is basically a idea of, in general, if I were to take another sample of 752 people and get a new estimate P hat, it probably wouldn't be exactly 8.5% again, but the standard error tells me how much variation I can expect to change. And the fact that it is 0.01 doesn't mean that it can only vary 1%. It doesn't mean that, hey, I'm always going to get an estimate that is at the lowest 7.5% and at the biggest 9.5%. It is just a measure of, on average, how much I expect it to vary. And in fact, because we now know what the central limit theorem is, and we know that in this case it holds, I can actually talk specifically about what that means, right? Because since the central limit theorem holds, what that is really saying, let me erase all my stuff here, is saying that of all the estimates that I could get, right, if I just kept taking an infinite number of samples of 752 people and kept taking different estimates, I now can say that those estimates will be distributed according to a normal distribution centered around 0.85 with a standard error of 0.01, right? So if I were to look at all of my possible estimates, they would be centered around 0.085, right? Where this x-axis represents all the possible estimates I could get, right? And so what this means is, yes, there is a probability, it is possible that maybe I get an estimate as low as 2%, but there's a very small probability that I would get an estimate as low as 2% or lower, right? It's the idea of, like, if I flip a coin 200 times, yes, it's possible that I get 200 heads in a row, but there's a very small probability, right? And so this gives me a way of measuring how probable different estimates are, how much variation there are in my estimates. If my standard error that I calculated was even smaller, then that means I would have gotten a distribution that looks, more scrunched up like that. So there would be all of my estimate. I would expect estimates even closer to 8.5%. So I'd be more confident in that answer. So that's kind of the general idea of what the standard error is. We talked about that last week, but I wanted to kind of re-hit on what that meant. So before we move on, I really want to make sure you guys understand what the standard error means and what it measures. So if you're still a little foggy, now's the time to ask. Doesn't mean you can't ask again on Wednesday or any other time, but I just want to put that opportunity up here now before we move on and start using it.
Sure, I had a quick question.
Yeah, shoot.
So what was the significance of the value 0.02 that's graphed on the left side?
Oh, that was me just trying to say a way to describe what's happening in this probability distribution is it's saying that any estimate is possible. It's just some are very unlikely to get. In the same way, if I flip a coin 100 times in a row, it's possible that I get anywhere from 0 to 100 heads, but certain values like 0 and 100 are very low. So on here, this distribution is saying if I picked some possible estimate that I could get, for example, I just picked 0.02 at random, it is possible. This is saying it's possible that I could get a estimate where it said 2% of the people, it estimated 2% of the people would register. But based on this distribution, the probability that I got 2% or any estimate smaller than that is that very small probability represented in that tail. So it has no special meaning. I was just using it as an example. Does that answer your question, or did I miss what you were asking?
Yes, sir. Thank you.
Awesome. Okay. So as always, yeah, go ahead. What do you got?
Same thing. So the standard deviation or standard error value that we obtained at 0.01, when you graph it onto that normal plot, it's off of what value?
So if I have, let me make sure I understand. So sorry, I just deleted everything, but so if I do this, and let's assume that's normal, like my drawing skills are, my wife's the one with an art major, although she also has a math major, so I guess I don't have any excuse. So if this is 0.0085, then the standard error is, remember, the standard error is a measure of how spread out the normal distribution is. So the smaller that standard error is, the narrower and higher it's going to be, and the bigger it is, the more spread out it's going to be. And so in general, it just means that if this is 0.01 and this is 0.01, we can start, it tells me, gives me a measure of how spread out things are. Like when we learn the 68, 95, 99 rule, we learn that if you go out one standard deviation in each direction from the mean, that accounts for 68% of the probability. So without doing any additional math, I could say that there is, since one standard deviation in each way would be 0.01, I could go 0.075 and 0.095. And as a quick and dirty estimate, I could say, hey, if I took an infinite number of samples of 752 people, 68% of the time, I would expect to get an estimate between 7.5% and 9.5%. Does that help kind of put the standard error in context?
Yes, sir. That makes sense. Thank you.
Awesome. Okay. So now we're going to do the very first new thing for this week that we didn't talk about next week, and that's calculate the margin of error, right? And so the margin of error is, it's based on Z star and the standard error. And the standard error we just calculated. So really what Z star is, and we'll talk about how to calculate that in a second, but it is how many standard errors do I have to go in each direction to get my confidence interval? Because I can just kind of skip to the end here, and the spoilers is what we're going to do is, if you imagine a number line, and this is our estimate right here, 0.085, right? To build my confidence interval, I'm going to say, I need to go how many, in this case, we're going to call it Z star standard errors to the left, and then I'm going to go that same Z star standard errors to the right. And this interval is going to be my confidence interval. So I'm going to, using my standard error, I'm going to calculate a Z star to say how many standard errors do I have to go out on either side of my estimate to be, in this case, 90% confident that my real value is somewhere in that interval, right? That's what we're doing. And before we look at any of the math of it, let me ask a general question. So, Allison, you online? And I forget. I forget. Do you go by Allison? I've literally got like 3 Allisons I'm teaching now, so I forget. Do you go by Allison or Allie or what?
I do go by Allison, sir.
Excellent. Okay, so let's just pretend I was right to begin with, and not that I was unsure of myself. So let me ask you, and don't worry about math. Just kind of think about this for a second in common sense. Or maybe it's not so common. Maybe I've just done this for so long. But if I have a confidence interval, right? I am saying I am 90% confident that the real answer is somewhere in this range. If I want to be more confident that the actual number is somewhere in the range, do you think I would make the range bigger or make the range smaller? Which thing would, which adjustment to the range would make me more confident that the real value is somewhere in that range?
You would make the range bigger.
And she's exactly right, because if you think about it, right, all things being equal, the bigger the range is, the higher a probability that my number is somewhere in there, right? So I can be more confident. And so you might think, well, more confidence is always better, right? But there's definitely a limit, because I could say, going back to me being elected, I don't know what I'm running for, but I could say, hey, we took a new poll and we are 99.99% confident that the number, the percentage of people who voted for Colonel Richards is somewhere between 2% and 98% of the population. Well, awesome. You're really confident, but you're really confident in a really big range. So who cares, right? And so that is what a lot of we're going to see for the rest of the semester is there's this balance and trade-off of you want to be confident, but you also want a small range and you can't have everything. And so you got to find that balance, right? I can have a really small range, but then I am probably going to have a very low confidence, right? Now there are things, and we'll talk about this more later, there are things I can do to change that. For example, right here, you can see that my range is based on the size of my standard error. So if my standard error was smaller, then my range would be smaller and I'd be just as confident about a smaller range. Well, this is my standard error right here. And so this n is on the denominator, which is my sample size. So if I made my sample size bigger, then my denominator would be larger and that number would get smaller. So by taking a bigger sample, my confidence level or my interval gets smaller, which makes sense. The bigger my sample I have, the more I can narrow in, right? But again, it's that trade-off. Oh, then I want to make my sample size bigger, bigger, bigger. But the bigger my sample size is, the more it costs. And so we'll talk about some of those trade-offs later, but I just kind of wanted you guys to think about that general idea of what we are doing here. So before we finish off this, any questions about what we just talked about and what Allison was pointing out about the size of a confidence interval and how it relates to the confidence level that we're talking about? Okay, so how do we find Z star, right? And so real bluntly, the way we find it is we can do it with this Q norm function. And we'll talk about it different ways, and I put over to the side that this is for a 90% confidence interval because I wanted to make sure you understood that this was not a typo. Yes, we are looking for a 90% confidence interval, but the way we find the Z star for it is with Q norm of 0.95. So a couple of things on this. First of all, quick refresher as a reminder on Q norm. Q norm is a function where I give it a probability and it gives me the value for which below which there is that probability of below which that number I have that probability of getting a number below that. I tripped over my words. I'll draw a picture here in a second to explain it. The other thing is that normally when we've done Q norm in the past, we had to give it a after that 0.95 comma the mean comma the standard deviation. When we leave those out, that means that I am using the standard normal. So I could have, instead of this, I could have longhand written Q norm of 0.95, comma, mean of 0, comma, standard deviation of 1. That would be the same thing. Because since I am trying to get my Z star to be a count of how many standard errors I want, which standard error is just a specific form of standard deviation, I need a count of standard deviations. In the standard normal, standard deviation is 1. So if I find the value in that standard normal, it will give me the count of standard errors that I need in my situation. Now, the reason that I do the 0.95 is, here's the scenario that we have. I'm going to try to draw in the space I have left here, right? So here is my normal distribution, and I am centered around here. And I'm what I want is, I want to know what is my confidence interval. I want the lower bound of my confidence interval and the upper bound of my confidence interval. And so what I want is I had a 90.
Sorry, I'm having trouble.
That's because no one's talking to you. What I want is I want a situation that between these two values, there is a 90% probability that I get something between those two values, right? So I want the upper and lower bound that makes that true. Well, since this is a normal distribution and I know it is perfectly symmetric, if I want 90% in the middle, that means that I have 5% in this tail right here, and I also have 5% in this tail right here, okay? And so what I would like to do, this value right here is my Z star number, right? And so that is the number I want to fit. I'm in a standard normal, so this is 0 right here. And that Z star is going to be how many standard errors did I have to go to the right of the center in order to capture 90% on each side. Well, since Q norm finds the total probability of being less than or equal to, I need Q norm of all of this, which is 90 plus 95. And so that's where I get the Q norm of 0.95. Q norm of 0.95 is going to capture me this number right here, which is the number of standard errors I want to be to the right, which is what I want to figure out. Someone actually in the last class said, well, what if I just did Q norm of 0.05, meaning I found this value right here? Well, you could definitely do that, but that would just be the negative value. So that would get you, instead of 1.644, that would get you negative 1.644. So you're happy to use that as long as you remember that we want the number that I need to go to the left or right. So I just need to make that positive. So that is a kind of quick primer, and I have code for this whole problem that we are going to work through when we are done here. But before we get there, what, if any, I know I stumbled on my words about halfway through there, so I'm halfway expecting some questions here. So what part of that does or doesn't make sense, or that I can re-articulate better? Now someone, go ahead, do I hear a microphone?
Sir, if looking for the 90% confidence interval, wouldn't we have to subtract the 5% on the left side?
You said, I'm sorry, you said if we were trying to find a what percent?
The 90% confidence interval, wouldn't we?
This
have
is
to
a 90.
subtract- wouldn't
No,
we have to-
this is, go ahead. We are finding a 90% confidence interval.
Okay, so I was just confused because we're only excluding 5% right now on the right side, and so
So
we
you're
have to-
exactly right. So we're excluding it. I only care about 90%. I'm excluding both the left and the right, but I'm just trying to find this number, because ultimately what I want is this number and this number so I can find this range. But since this is 0, I'm doing this in the standard normal. By getting that right number, I now know that when I do my range, I'm going to go that far to the right and that far to the left. So I'm just doing this to get the number, and then I will exclude both the lower and the upper tail. You're right, I do need to exclude both of them, but I'm just getting the number of how many standard errors I have to go to the left and the right. And since this is just the negative of this, once I have that count, as we see, I can construct my margin of error to go to the left and the right of it and exclude both tails. Does that get what you're asking?
Yes, sir. Thank you.
All right. And he brings up a good point, right? Of also saying, well, what if it was a different percentage, right? I can do this for any percentage. If I said, hey, let's find a 70% confidence interval, I would do the same setup and say, okay, well, then I want a scenario where I go like this and the middle is 70%, which means I have 30% that I have to distribute in the tails. So I got 15% there and 15% there. And so to find this Z star, I would do Q norm of 70 plus 15, which would be 0.85. And that's how I would find the Z star for a 70% confidence interval. Rarely in the real world does anyone care about 70%, but you can find it for any percent, which actually brings up a good point as kind of a side note. You can find a confidence interval for any percent. You can find a 90% confidence interval, a 91% confidence interval, an 83.5% confidence interval. However, when you're trying to say you're confident about something, you usually want to be pretty confident. So in the research and statistics community, usually you will see either 90, 95, or 99, because everyone has kind of decided those are all pretty good of increasing confidence, and so they've just used those. So you, because as we showed here, this number only depends on that number, the Z star for all 90% confidence intervals is 1.644. And so there, because that is saying that a lot of statisticians like myself have just memorized what those numbers are. So you may come across times in the book where they say, all right, now we need the Z star for a 90% confidence interval, which is 1.644. And you might say, you skipped over the part where you calculated it. That's because they're just saying, hey, we just have memorized that for 90%, it's 1.644. For 95%, it's 1.96, right? And so you can still calculate it directly, and I want you to be able to, but understand if they skip over it, it may just be because they have assumed that people have memorized what it is for 90, 95, and 99, because it always stays the same. But you can always calculate it directly, and that's kind of what I want you guys to be able to do. So with that, our margin of error is 0.017, right? Because that's 0.01 times 1.644 about. And then I can do my last part, which is just saying, so therefore I am 90% confident that the actual parameter P is somewhere in the interval of my estimate minus that margin of error plus the margin of error. And this comes back to what Andrew was saying, right? Is that I got my margin of error, but then to make my range, I went that far to the left of my estimate and that far to the right, or below and above, right? And if I calculate that directly, that means that my interval is from 6.84% to 10.2, right? Because this is my estimate. So 8.5 minus 1.7 is about 6.84%, and then plus is 10.2. So what I can now say to the guys in charge is I can say, hey, you wanted to know what percentage of people would register for your website. I'm not going to tell you I know the exact number. However, I can tell you I am 90% confident that the actual percentage of people who will register is somewhere between 6.84 and 10.2%. And the most likely answer is they're going to say, oh, that's definitely great. We just wanted to make sure it was above a certain number. But as long as you're 90% confident somewhere in that range, we're going to invest. Maybe not. Maybe this is something really specific and they need to know more. And they go, oh, we were really hoping you were going to be able to narrow it in a little bit closer, maybe within 8 to 9%. And I say, okay, well, I could do that, but we're going to have to take another sample, because if you want the range, if you want the interval to be smaller, I'm going to have to get a bigger sample size. And maybe they'll say, oh yeah, because we're going to invest $1 billion if this is true, or if we feel confident about it, but we can only, doing a bigger sample is only going to cost us $10,000. So we're happy to invest $10,000 to be more sure about that. And that kind of thing happens all the time. Okay. Before we jump into the code, any questions on kind of the large picture here of the steps that we followed to get this confidence interval and what it actually means to us and why it is a powerful thing to explain the power of our estimate to something? And I should have used the word power, because power is going to be something later in this semester, but how certain we are. Awesome. Okay, so let's go over to my code. And as a reminder, I always put all of my slides and my code on the All Students page. So if you go to All Students and go to Files and go to Instructor Pages and go to me, my slides that we just saw and all of this code will be up there. I highly recommend and encourage you to download this, mess with it and toy and see what makes sense and doesn't. And if you learn something, cool, let me know. If something on there you did and it didn't do what you expect, bring that as a question. We can say either how my code is bad, or I can say, oh, here's how, here's an interesting thing you showed up. So I'll use it. And as a reminder, everything in this class is open book, open notes, and open code. So you are more than welcome to use this code on test. That said, I'm going to give you the caveat. That's why I said play with it and make sure you understand it. And if you do use it, I suggest editing it and cutting it down and making comments that make sense to yourself. Because the people I've seen with the biggest problems are the people who go, oh, I need to know confidence intervals for the GR. Oh, but Colonel Richards made code. I'll just download it. I don't have to think about that again until the GR, because I have his code. But if you don't know how to use it, that's like saying, all right, I'm going to have to be a sniper, but the sniper rifle comes with the instruction manual, so I'll just wait till I'm deployed downrange, and then I don't have to practice using it, right? You need to know how to use your tools in order for them to be of any use. So highly encouraged and welcome to use this. Make sure you understand it and make it your own. Okay. With that in mind, this is, like I said, the exact same question that we just answered. But what we're going to do is go through what's called the prepare, check, calculate, conclude process, which is a process the book introduces, and it's how it works through these type of problems. And it's something we're going to use as we go into the labs, because this is all the things you would have to do anyway, but just organized in a way so that we can more easily understand each other's examples. You can understand mine and I can understand your work back and forth much easier. So the first step is the prepare step, which if you've ever watched cooking shows, because I will admit my wife and I are both cooking show addicts, not like competitions, but just shows where they make food and then they eat it and they say, wow, this tastes delicious. It's how I survived my first deployment. I watched cooking shows every time after I went to the chow hall to go back and go, oh man, that would be cool. All right, let me eat my Rice Krispies. And so what they do is this thing called mise en place, and that's where they, it's like their setup where they put all their little ingredients pre-measured out and everything, so that they know where they're going, right? And that's why they can make their stuff so much faster than you, because it's all their ingredients are set out, right? And that's what we're doing. Our plan is that we are going to cook. We're going to cook up a confidence interval, but we're going to set up all of our ingredients first in the prepare step, right? So the first step is identify the p hat. Now, since this is the example we just went through, I'm not going to explain the example as much, but I'm going to show the code for it. So the p hat is our estimate, right? And so we had our sample size of n equals 752, and we said 64 people did register. So our estimate is 64 divided by that, and we can run that and say, lo and behold, 0.085, that 8.5%. That's our p hat. That's our estimate of the p, right? And the nice thing is, I have saved all of these in memory so I can use them later, which, side note to you guys, when you're doing your labs, I'm all for you saving numbers as variables, but if it's something that I need to know, you need to then write it again here so it outputs to the screen, because I can't tell you how many people I've had to knock off a few points on labs because you calculated it, but then you stored it in a variable that I have no idea what the number is. I need to know what it is to know if you're right or not. So spit it back out so I can see what it is. Then we said our sample size is 752 and our confidence level, the question said it has to be 90. Side note, like I said, I encourage you guys to download this and play with this, but based on a confusion I had from someone else, I'm going to just say this so you guys don't make a mistake. You can definitely go in here and say, I wonder what happens if the sample size was, 7,520 and change it like that. And it will change all of the numbers. What it won't change, though, is this text. I want to make sure you guys understand. This is not code. This is just stuff I wrote. So I've had people go, well, I changed this to 7,520, but it said our estimate was still 8.5%. I don't understand how that makes sense. Well, that's because this down here is like a handwritten note, right? This will change the code and the output, but it can't change what I just wrote as words. So just be aware of that. You can definitely change it, but I didn't write this so that it changes my report as well. Okay, so then we're going to go down to our check, right? And our check step is, this is checking the conditions of the CLT, the central limit theorem. We've got two, right? The first one is, are the observations independent? And that is just as simple as saying, yes, the problem states that they came from a random sample. If the problem didn't state that, then it doesn't mean we're not going to do the rest of the problem. It just means here I would write, we cannot know until we determine that the sample came from a random sample. Or if there's something in there that makes you believe that it's not independent, then you would write, no, it does not seem that they are independent because of this. We should be suspicious of the results until further research can be done. Some kind of caveat like that. So either you need to say here why they are independent, or you need to add a caveat of why you think they may or may not be. You got to say one way or the other, but they are, so we're good. Then our second one is it large enough? Which, like we said, is to check these two inequalities here with P. We don't know what P is, so we are allowed to use P hat to estimate it. And so we can make R calculate that because I am lazy. And I get 64 and 688. Those are both definitely bigger than or equal to 10. Last time I checked, I can get my calculator out if you guys don't believe me. But they are both greater than or equal to 10. And so therefore, our second condition, our sample size being large enough, is met. So our two conditions are met. So we are good to go to use the central limit theorem. So before I move on to the calculate phase, anyone have any questions about the prepare and check, what we did in there? It's everything what we did on the slides. It's just now we're doing it kind of formally in our code. Any part of that need more explanation? Okay, so now we're going to move into calculate. So the first thing we're going to do is find the standard error. Now, I assumed you guys were probably not going to knit this and you were just going to look at this in code. And so rather than make a fancy looking equation that would look nice in the knit, I did this thing where I tried to draw with characters what the equation would look like so you could see it in the code. If that's helpful, awesome, let me know. If it's annoying, let me know and I will stop doing it. But I wanted to make this something that you could see in the raw code. So our standard error, like it says, we usually use P, but we don't know P. So we're going to estimate it with P hat in this equation. And then down here, this is just that equation, but coded in R, right? You can read through that. And that is just doing that square root with all the P hat. So I can go ahead and run that. And not surprisingly, there is our value that we got. Our standard error is 0.01. And then a bunch of numbers, which I only usually care about 0.01, but since I'm making R remember it, I figure it might as well just keep all these exact numbers. If I'm going to round something, I'm not going to round it to the ends. I'm just going to let R, it's happy to memorize 1,000 digits, so I'm just going to let it keep doing that. Okay, so now we need Z star. Now, this line right here, line 66, says to skip to line 96 for the Z-score method. That's what we just did on the slide. And that's what I would recommend if you're that you focus on. You can skip all of this right here. This is basically a little bit more for those of you who are interested in seeing a little bit more behind the scenes of why this works or what another way is equal to. Then by all means, read through that and see how you get the same answer this way. But if you are holding on by the seat of your pants and you don't want to, you understand what's going on, feel free to skip all of that. If you're making your own version, delete all of that. Just keep the parts that make sense to you. But skipping down to line 96, here is the Z-score method that we talked about, right? Where I say, hey, I'm going to figure out how many standard deviations, and we say, since we want a 90%, we need to go to the 95th percentile. That's basically what we were drawing in that picture when Andrew was talking about that, right? And so by doing Q norm of 0.95, I even made this comment to myself to the side to make sure I know, oh, that's not a typo. I really do want to do 0.95 for a 90% interval. And I can run that. And there we go, 1.644. And that's always going to be the case for a 90% confidence interval. And so then I can go down here and say, okay, so now I'm going to put it all together. So I'm going to set Z star equal to that value that I just found there, calculated the same way, right? And then to find my lower and my upper limit, I'm just going to say, take my estimate and go Z star standard errors to the left, P hat minus Z star standard errors. And then my upper limit, go P hat plus Z star standard errors, that many to the right, correct? And so I do that and I have it type out the confidence interval is 0.0683 all the way up to 0.10. Like we saw, about 6.8% all the way up to about 10.2%. That is my confidence interval. Now, if it helps, great. If not, don't worry about it. I included here a block of code that you definitely do not need to understand if you don't want. I put comments in here mostly for myself, but you can look at them too. But you can use this without understanding it. What this is this is just code that draws a nice picture to try to help us make sense of this. So if you run this code, and again, if you're making your own, feel free to delete it if you don't want to confuse yourself. It draws this nice picture of what we're doing to try to tie it all together, right? And so it's saying what we were doing was we said we took an estimate and we found that estimate to be 0.085. And because we showed that the central limit theorem conditions were met, we know that all the estimates that we could get are distributed around that 0.085, which is that red line, according to a normal distribution. And what we wanted to find was, we wanted to find that confidence interval, that range depicted at the bottom by that green line, right? Of saying, from where to where do we have to go to ensure that there is a 90% probability, right? If we integrate over that confidence interval, we get 90% in that area, which means there is a 90% probability that we will get an estimate somewhere on that green line, right? And we figured out that green line range by saying, to ensure that we have 90% probability of getting an estimate somewhere in that range, we have to go Z star standard errors to the left of the red line, which is our estimate, and Z star standard errors to the right of that estimate. And that is how we built our confidence interval. Before I move on to the last conclude, does anyone have any questions about how to interpret this picture and what's kind of going on here? Okay, so the very last step is this conclude step, right? If this is the cooking show, we've put all of our ingredients, explained why it should work, and now we're going to put it into the oven and hopefully conclude with a cake and say, here is the reason, here's what it all means, right? So here is all of the summary of just all of the numbers, statistics that we calculated, right? But this is tying it all together of what it means, right? And so what this is saying is, hey, our original goal was to try and determine what proportion of visitors to a website would become registered users if we switched to a new site layout. We didn't want to show the entire population the new site, so we took a sample of just 752 people and found that out of that sample, 8.51% of them registered. So using that as an estimate, we found that for a 90% confidence interval, our estimate had a 0.016 and a bunch of numbers I don't care about margin of error, meaning that we are 90% confident that the actual proportion, the number we don't know of the population who would register, is somewhere between 6.837% and 10.184%. And really, like I said, I made this all a little bit wordier because I wanted this to stand alone and have something for you guys to read. But really, I would say that this part right here is really just the meat of the conclusion, right? That doing all of that is so that we can say, I am 90% confident that the actual proportion is somewhere between 6.837 and 10.184%. That is the take home. That is our conclusion. That was the whole point of what we did everything. That's what I would tell to the executives who asked me, hey, should we deploy this new site? Okay, we got about 5 minutes left. What, if any, questions do you guys have, or is there any part of this code or the slides that you guys would like me to scroll back up to so we could take a second look at or focus on or talk about? What do you guys got? Okay.
Sir, if no one has specific questions on this class, could I ask a homework question?
Sure. Yeah. No. By all means, it's your time. If you got a homework question, before I hit that, let me just say real quick. If you don't have this, like I said, I highly recommend download this, play with it, make sure it makes sense. If you get a result as you're playing with it that doesn't make sense, bring that on Wednesday, because we're going to start with this and go into Wednesday's lesson, which is really kind of the other side of the coin of this. And so those questions will feed really well to get us into lesson 5. But like as I said, I'm more interested in making sure you get the homework and the lab done before then. So going back, what is your homework question?
Yes, sir. On lesson 14, question number 4, it's about the drummer. He has a 99%
Sure.
efficiency. If he has 700 beats, what is the probability that he misses no more than 10 times?
Mm-hmm.
I thought I'd use like an R code or
Yep.
P binomial, but that was like
Sure. Yep. I agree. All that sounds good so far.
So, but I did P binomial, Q equals 10, size equals 700, and the probability of 0.99, but I wasn't getting an answer.
So I would say without going into the details, it sounds like the main problem you're running into is that you are trying to find the probability that he misses a certain number of times, but you were using as your probability the probability that he hits. So if you want to do p-norm based on the number of misses, then you are now defining success as missing. So you have to use the probability. What's the probability that he misses a beat, which would be the complement of 99%, right?
Yes, sir. Originally, I was going to do 1 minus that code. Would that not?
So
give
if you
me
wanted
the
to do
same
1
thing?
minus, then you have to do it so if you want to do 1 minus, that's fine. But then you have to change, instead of saying using 10, you are now talking about him hitting beats. So you have to restate the question as, what is the probability that he hits? If he's going to miss 10 or less, then that means you want him to hit 689 or more, or 689 or more. I have to check my code, but you either have to change the probability to the probability he misses, or if you're going to say hitting, then you have to change the question to be in terms of how many he has to hit.
Okay, I'm tracking that, but would I use like P norm or would I use P binomial?
Oh, great question. Definitely P binomial because this is a binomial. We have a certain number of options and a certain number. So if you use P norm, you'd have to have a mu and a standard deviation, and you could definitely figure those out, but they would be estimates. To get an exact answer, you definitely need to use P binom because the number he hits or misses is a discrete number. He can't miss. He can't hit, 75.32 beats. And so as such, it's not normal, it's binomial. The normal will give you a pretty good estimate if you do everything right because the one kind of converges to the other. But you're right, you should definitely be using binomial in this situation.
Yes, sir. Thank you. I just thought I heard you say P norm.
I may have because I've been spending this entire course or lesson talking about normal. So if I said normal, I apologize. That was a good catch. That was wrong. She is right. It is binomial. It is not normal. Yeah, what do you got? Joshua,
sir,
I forget what you go by, sorry.
I go by Josh, sir.
Excellent. What do you got, Josh?
The assignment for Lab 5 still isn't up yet. Do you know when that will be?
It should have been up for the last 6 days. Oh, you know what I just realized is it is up, but because Captain Forbes is not around, he did not make an actual assignment. I need to do that. I apologize. So it is sitting, all of the files for it have been sitting since last week in the, if you go to all students under the files, under labs, everything you need there is there. But you're right, I should have, when I made an assignment, it only went to my students, not his. So I will, as soon as I will try at lunch here to make the assignment. But in the meantime, like I said, I made a post last week saying that they were available up there. If you're not seeing them, then that's a larger issue, but they should be sitting there under the files section.
Yes, sir. I have the lab done. I was just talking in terms of the submission.
Oh, okay. Yes. Okay. Good. Excellent. Okay, good. Then yes, I will make I forgot that I am Captain Forbes' surrogate, so I will do that. Also, I just realized we are just 1 minute over, so I got to make sure none of you guys feel compelled to stay around. I will stick around for a couple of minutes if anyone has any questions, but otherwise, get out of here. Look at this stuff, think of your questions, and then I will see you on Wednesday, if not before then. Okay, sorry, I had to get that out. But yes, Josh, I will make that. I will go. I think I have the authority to go into Captain Forbes' team and make that assignment so you can turn it in. I'll try to do that at lunch here.
Thank you, sir. Also, I was just looking at the My Open Math, and the lesson 16 homework is not in.
Correct.
Okay.
I just want to make sure. It is not up. No, I apologize. I am. That's on the course director, which unfortunately is also me. But with Captain Forbes being gone, I was originally doing everything a block ahead. Then I was doing it a week ahead. And I've been, over this last 2 weeks, I've been doing everything about 24 hours ahead. So I am finally catching up. But yes, I will hopefully by tomorrow make sure that the next several homeworks are posted. So I apologize that I am, that you're dealing with that. That's on me. And I will get it up there.
No worries, sir. I just want to make sure I didn't have any issues technically.
Yeah, no. I didn't share it with everyone but you. That sounds funny, and I might do that in the future, but I didn't do it this time.